Okay, now, thankfully for you guys, the only log functions we're ever interested in differentiating are the ones with a natural base, okay? Which is just as well for you, because the other ones are a mess. Do be wary though, on your calculators, if you've got them there, okay? You've got two buttons for logs, right? You've got this button, log, and then you've got probably one next to it which says ln, right? Okay, now, here's where it gets really confusing. On your calculator, and only on your calculator, this means log base 10. Okay, which is why I think if you look above this button, okay, I think it'll say 10 to the power of x. Okay, because that button's really about scientific notation. There to help you out with your, your chemistry stuff and working out concentrations or whatever you do for titration. I don't know. I never did chemistry. But that's log base 10. Okay, only on your calculator. Everywhere else you see there's the word log written. If you see it in a textbook, if you see it in an exam, if you see it on my board, what we really mean is log base e, because that's the important one. Okay, so what we really mean is this. Okay, so if you ever see log in an exam, please don't press your log button on your calculator because it's a totally different base. What we're really after is this one. Okay. All right, now that was my preamble. Let's have a look back at differentiating this thing. Okay, you remember so many questions in maths boil down to trying to turn a problem that you don't know how to solve into a problem that you do know how to solve, and then you work with it. Okay. So what could I do to this equation to change it into something that looks a little more familiar? Yeah, this is a log equation, and logs and indices are really just opposite sides. Okay. So if I were to rewrite this, I would say x is equal to e to the y. Is that okay? Does that make sense? This is very, very, very similar to what I have over here, right? Except it's just a different variable up there. Now, because it's just a different variable, instead of working out dy on dx, which is what I have when it's like y equals something, I'm going to work out dx on dy. Okay? With these letters, I can just switch them. dy on dx, it's just a fraction, just like any other. Okay? So when I differentiate it, I'm differentiating e to the y with respect to y. Now, you know all those questions? They just put different letters in there, like s squared plus s, differentiate with respect to s, or differentiate with respect to t, whatever. They're just letters, okay? So when I differentiate this, it follows exactly the same rules as this. The only difference is it's a y. So what do I get? I get e to the y. Hasn't changed. Now what I was really after, right, was not dx or dy. I want dy on dx. And we said this is just a fraction, right? So if I've turned this side upside down, I've taken the reciprocal, then I should take the reciprocal the other side, right? Yes? Does that make sense? One more step. E to the y, right? E to the y is actually just x, right? That was the substitution that I made. So therefore, this derivative is 1 over x. Okay? So, get out another color, get red, blue, green, whatever, and put some big boxes around these two results. E to the x, you differentiate it, you get it back. Okay. Log x, maybe I should put that up front. The derivative of the natural log is 1 over x. Okay. Now let's just think about that for a second. Let's, you know, I'm a big fan of this. Let's apply some intuition. Okay. What does the log function look like? Okay. It only exists for x is greater than 0, right? And it's like an exponential that's just been twisted over. Okay, so you get this kind of shape. Okay. Now, how would you describe its gradient? Well, it's kind of the opposite. It's this gradient is kind of the opposite of the exponential one, right? It's always increasing, it's monotonically increasing, but instead of getting faster and faster and faster, it's getting slower and slower and slower. Okay? So that's what the gradient looks like. Well, let's think about what this looks like, 1 over x. You guys know what 1 over x looks like. You've been graphing that for years. What does it look like over here? It looks like this, doesn't it? At least on this side. Okay? And that's exactly what we've got. Number 1, this gradient is always positive. And that corresponds to the fact that this graph is always increasing. Okay? Number 2, the gradient is getting smaller and smaller and smaller forever. Okay? Which corresponds to the fact that log x is getting slower and slower and slower forever. Does that make sense?